So here's some basic rules to follow when you draw Lewis structures. So Lewis structures are representations of a geometry of the molecule. We're focusing on covalent compounds now between nonmetals and nonmetals. So here we're trying to devise the structure of a molecule utilizing single bonds, double bonds, or triple bonds. So to get the correct Lewis structure, you have to follow two rules. They are not equally important. This one, rule number 1, is actually much more important than rule number 2, because in rule number 2 you can have what's called an expanded octet. That is to say, you can have atoms that have more than 8 electrons around it. We'll go over some examples through these series of videos. The first and foremost rule, the most molecular structures would like to minimize their formal charge. Formal charge is what Fc stands for. The formula for formal charge is what the atom is normally happy at, minus the number of electrons around the atom. So if you can satisfy formal charge minimization and get the atom to have the octet rule, meaning having 8 electrons around it, then that's really a superb representation of the structure. Before we actually make and draw these Lewis structures, and don't forget they have 3D representations, we have to go over some ground rules. First ground rule is carbon. Carbon loves 4, so carbon is happy at 4. So I'm just going to put happy in quotation marks. And not just happy at 4, it absolutely loves 4. Okay, so carbon loves 4. What does that mean with carbon is happy at 4? So that is to say carbon will have 4 valence electrons around it. So each of these dots represents 1 electron. But instead of showing it like this, I'm going to show it another way, in that the carbon, you see this electron is ready to form a bond. This electron is ready to form a bond. And same thing with these other 2 electrons. So I'm going to draw it like this. Carbon forming a bond here, and bond here. And let's not worry about the substituents, the R groups. That's just an atom or a collection of atoms. It could be the same atom. It could be a different atom. Really the focus is on carbon. So carbon would love to be at 4. So this is what I mean when I say minimizing formal charge and having an octet rule. First, let's look at the octet rule, though formal charge is more important. So octet rule. Here we're going to count both shared and unshared electrons around the central atom. Okay, so the central atom here is what we're talking about, is carbon. Okay, let's not worry about the substituents. We will not care about that. But we're only focusing on the carbon. So looking at the octet rule, it's going to be 1, 2, 3, 4, 5, 6, 7, 8. So the octet rule is balanced here. It's correct. And then formal charge minimization. So this is how you do formal charge calculations. 1, 2, 3, 4. Okay, you have 4. Carbon is happy at 4. The number of electrons around the atom, 1, 2, 3, 4, is 4. So carbon happy at 4 minus the 4 bonds around it. The formal charge around this carbon is going to be 0. Okay, let's do some specific concrete examples. So let's replace the H's with hydrogens. We have the molecule methane. Methane 1, 2, 3, 4, 5, 6, 7, 8. The octet rule is good. Formal charge 1, 2, 3, 4. Carbon is happy at 4. 4 minus 4 is 0. So the formal charge of this carbon atom is 0. In fact, methane, CH4, really has no charge associated with it. And that's because this is the best representation of CH4. Again, the focus is on covalent molecules. So carbon loves 4. That doesn't mean we always get single bonds. We can also accommodate double bonds. So let's give an example of formaldehyde. Again, our focus is just on the carbon. Okay, so this is the molecule formaldehyde. Again, I want your attention to be just on the carbon because we're studying carbon here as the framework for the ground rules. So formaldehyde is the name of this molecule. So 1, 2, count everything now, 3, 4, 5, 6, 7, 8. So the octet rule is satisfied. The most important rule, though, is formal charge. All right, so here we go. 1, 2, 3, 4. Carbon is happy at 4. 4 minus 4 is 0. The formal charge on that carbon is going to be 0. So this would be, at least for the central atom carbon's sake, the best representation of the structure of formaldehyde. Okay, here's an example where we use a double bond for carbon to get 4. Let me give you an example of a molecule that carbon utilizes a triple bond, and that's cyanic acid. So the structure of cyanic acid is HC triple bond N, or HCN. Again, we're going to focus now on the central atom carbon. Okay, that's what this whole video is on, carbon and carbon alone. We're first going to do, let's do the most important rule, and that is formal charge. All right, so here we go, formal charge, 1, 2, 3, 4. Carbon is happy at 4. 4 minus 4, which is the number of bonds around it, is 0. So the formal charge around that carbon in cyanic acid is going to be 0. Let's look at the octet rule. Okay, now you're going to count shared electrons. You see this single bond is shared between this carbon and that hydrogen, but it's shared. And so we're going to count those as 2 for the octet rule. So here we go. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the octet rule is satisfied. The formal charge at 0 is minimized, and that's a good representation structure for cyanic acid, which is HCN. So carbon has to have 4. It could be through single bonds, it could be through double bonds, it could be through a triple bond, but carbon must have 4 bonds around the substituents, which are the outer atoms. Here we're focusing on the central atom being carbon. Again, we want to keep in mind always, when drawing these structures, minimize formal charge, and try to get the octet rule, realizing that some atoms can have an expanded octet. Though the example shown here for carbon will not have an expanded octet because it so much loves 4.